Let's go over three principles about electrons. First is the Aufbau Principle. And the Aufbau Principle says that electrons will take the lowest energy orbital that is available. In an atom, that would be the 1s orbital. The next highest energy orbital is the 2s orbital. Then the 2p orbitals. There are three 2p orbitals, which can hold up to a total of 6 electrons, because each orbital can hold 2. Then the 3s orbitals are next and highest in energy. Then the 3p orbitals, then the 4s orbitals, then the 3d orbitals, and so on. This is why we fill the electrons in this order when we're writing an electron configuration. And the analogy that the part of the electron jogging tracks analogy you might have seen a couple lessons ago, the part of the analogy that fits here is that the electrons take the easiest jogging tracks that are available. The next principle is Hunds Rule, which was developed by Friedrich Hund, or as I call him, Fred Dog. And Hunds Rule says that for equal energy orbitals, each must have one electron before any take a second electron. And we stated in our electron jogging tracks analogy that there were, for example, three 2p orbitals, that each one of those 2p orbitals had to have one electron jogging on it before we could double up. And that was Hunds Rule. The third one is the Pauli exclusion principle, which was developed by Wolfgang Pauli, and it says that two electrons in the same orbital have different spins. And the part of the jogging tracks analogy that went along with this was that while any orbital, any track could take up to 2 electrons, those 2 electrons had to run opposite ways on the track. In other words, they couldn't run together, talking about last night's national championship game or something like that. They have to run opposite directions, and so they see each other 2 times every go-round, and all they can say is, "What's up, dude? Hey." That's all they can say because they're not running together. This brings us to orbital diagrams, which are very similar to electron configurations. Orbital diagrams show the spins of the electrons and which orbital each one is in. So, oxygen, if you look on the periodic table, oxygen has 8 electrons. A neutral oxygen atom has 8 electrons. So, we know that the first 2 electrons will go in the 1s orbital. So we represent this on an orbital diagram by showing an up arrow and a down arrow in the 1s orbital. Each of these boxes here represents an orbital. You can see for the 2p orbitals that there are 3 of them, which could hold up to a maximum of 6 electrons. Then the next 2 electrons go in the 2s orbital, and because of the Pauli exclusion principle, the 2 electrons in a single orbital have to have opposite spins. So we draw one arrow up and one arrow down. Then there are 4 more electrons, because there are a total of 8 for oxygen. And according to Hunds Rule, we have to fill up all of the 2p orbitals with 1 electron before we can add any second. So, for oxygen, the correct way to represent an orbital diagram for the 2p orbitals is to go up, 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 down. We don't go up, down, empty. That's wrong. That violates Hunds Rule. Let's try phosphorus. Phosphorus has 15 protons, so naturally it's going to have 15 electrons if it's neutral. So phosphorus goes 1s2, 2s2, 2p6, because we have to get up to 15 electrons. So the 2p orbitals are going to be completely filled, and here's how you do it correctly. You go up, 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 down, down, down. Now, Mr. B, I know that all the 2p orbitals are filled, so if I'm doing this on my homework, I'm just going to go for the 2p orbitals up, down, up, down, up, down, and you're never going to know. Oh, yes, I am. I'm a trained scientist. I can tell if you went up, 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 down, 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 or if you went up, down, up, down, up, down. No, I really can't, but you should get in the habit of doing it that way. Then we fill up the 3s orbital, up, down, and then that brings us to 12 electrons, and then we have 3 more, up, up, up.